Okay, kids, it's day 5, and I know you're excited. We're so close. I'm going to do this, review, and then review test, and then a short quiz / test for this. So all of this stuff will be eventually, and most of it already is at nkinfinity.com. Click on Teacher Resources, and you can find all of these videos nice and neatly in an organized fashion. All right, kids. Day 5. My name is Mr. Key for you. I am Mr. Krause. My partner in crime is Miss Vicky Newman, and we are NK Infinity. Oh my God, I am so tired. It's been a long day. Estimating with confidence. Huh? I don't got no confidence. It's math. I ain't got no confidence. You got confidence. All right, what must be done in order to reduce the standard deviation in a simple random sample? The only thing we can do to reduce the standard deviation, as we've talked about this before, is to increase the sample size. N. Okay. By what factor must the sample size be increased in order to have the sampling distribution? I've asked this question like 4 times. I don't know why I keep asking it. Increase the sample distribution in order to have the sample. So we got to increase by 4, because don't forget, we're going to take the square root. So if we take the square root of 4, that's equal to 2. And if you divide by 2, that's taking half of something. What is the formula for the standard deviation in a simple random sample when we are looking at sample means? Okay, so the simple is equal to this population standard deviation divided by the square root of n. Describe the empirical rule. Well, okay, the empirical rule is quite simply that 68% of the data is within plus or minus 1 standard deviation. 95% of the data is plus or minus 2 standard deviations. And it's not quite 2, by the way. It's 1.96 standard deviations. And finally, 99.7% of the data is within plus or minus 3 standard deviations. So that'll come into play today just a wee bit. If I told you that we were 8 plus or minus 1, 8.1 represents a 99.7% confidence interval, then then what do we know? Well, then the standard deviation, this represents 3 standard deviations. So I'd have to come over to my calculator. That's why I was looking. I didn't do the math. It's 8, what did I say? 8.1. Oh, I picked 8.1 for a nice reason. I don't know why I'm doing this. Divide by 3 is just 2.7. So my standard deviation is equal to 2.7. Okay? Because remember, I'm going 8. This is 3 standard deviations. Because it's 99.7, that's 3 standard deviations to the right. So if I divide by 3, 3 standard deviations to the right, 3 standard deviations to the left. That gives me my 99% confidence intervals. Confidence intervals have 2 parts. An interval computed from data. Oh, so now we're going to talk. An interval computed, an interval computed from data. And a confidence level that gives the probability that the method used produces an interval that contains the parameter. That contains the parameter. And you have to remember the parameter goes with population, right? It's not sample. Contains the parameter that goes with the population. The confidence level that the collector of data uses depends on how certain the study requires. That's not really good English. In most cases, 90% confidence levels or higher are used. Of course, the higher the confidence level, the larger the interval. It should come as no surprise that in order to be more confident about the true value of the population mean, or the parameter, we need to use a wider interval. It's kind of like if you had a fish. Let's say you had a fish swimming. Let's see if I can draw a fish. You got a fish, right? And you're like, okay, I'm going to send a net this big. I'm going to use a net this big. And I'm going to come in, and I'm like 50% confident I can scoop that thing up at one shot. And then the next person comes in and say, you know what, I'm going to use a net that's a little bit bigger. I'm going to use a net that's like twice as big. Well, I'm like, maybe this one I'm like 68% confident. And then if I use a bigger one that's like maybe twice as big, I say, hey, now I'm like 95% confident. And then you got this guy, he comes in, he goes, I want to be almost 100% confident, so I'm going to use one that's like 3 times as big, and I know if I just sweep it over, I will be able to grab that fish. Well, that's confidence intervals. And we're going to see what it looks like now on these charts, but I'm going to have to take a break first. I'll be right back. So in every case so far, and everything that we're going to do in here, our mu is unknown. Our population is unknown. But we want to cast a net. So if I casted it out 1 standard deviation plus or minus 1 standard deviation, I would be 68% confident. Maybe I should put that in here. If I cast it out 1, I'd be 68% confident. Now, if I cast that net out 2 standard deviations, 1, 2 standard deviations, and I go from here out, so not these, go from there out, I would now be casting it plus or minus 2 standard deviations, and I would be 95% confident. And if I cast it all the way out to here, I would be out 3 plus or minus 3 standard deviations. I'd be 99.7% confident. Now remember, our mu is unknown. But we're going to cast out a big enough net on these. These are all sampling distributions. These are all sampling distributions of x. Of x bar, actually. All right. So a 90%, oops, what the heck just happened? A 95%, 99% confidence interval for a parameter is an interval computed from sample data using a method that has a probability of 0.9, 0.95, 0.99 of producing an interval that contains the true value of the parameter. And the parameter, again, remember, is the population mean. The parameter, well, it could be the sample mean. No, the parameter, could this... We're really looking for a mean. Anyway, in order to find an 80 or 90% confidence interval, you need to find an interval that will catch the central 80% or 90% of the normal distribution of x bar. Another way to think about this is we want to get rid of the tails. Now remember, our table tells us about the tails, but we want to get rid of the tails. And we did a little bit of that in Unit 8. So let's talk about the procedure we're going to use. It's a very simple procedure. It's not difficult, but I want to make sure I walk you through it so you know how to do this. I can't pick up my notes for some reason. All right. 1, we want to take a sample and calculate x bar. So take a sample and calculate x bar. Let me do this in a different color. Take a sample. And calculate x bar. All right, so far so good. Choose a critical value. We're going to talk about that. Choose a critical value. We're going to talk about what that means and how we do that in a minute. Based on the confidence level required. Based on the confidence level required. And we're going to call that Z star. You'll see why in a minute. Calculate and interpret the interval. Calculate and interpret the interval. All right. Critical value, Z star, the number of standard deviations needed to capture the middle, 80%, 90%, 95%, whatever it is you're looking for of the sample distribution of X. So let's walk through it. It's pretty simple. Let's say we are looking for an 80% confidence interval of a normal sampling distribution of X bar. Remember, if we're looking for the central 80%, we're looking for the center 80% centered around X bar. So this is my sampling distribution. We're going to let this be X bar, which of course is equal to mu. X bar. And we're going to find the center 80%. So I don't know where that is. It's somewhere out here. And somewhere out here. Now the key to all of this is 80%. Well, if that's 80%, this part over here on the right and this part over here on the left, they have to add up to the missing 20%. And since I want this thing centered, this needs to represent 10% of data. And this needs to represent 10% of data. So what I want to do is I want to find a Z-score that's going to give me a 10% tail. So all I have to do is look up 1 because they're going to be about the same. So I got to go here in my table and I want to look up 10%. So 0.1000 if I can find it. I think this is it right here. That's probably right behind my head. 0.1003. So that's 1.28. So my Z-score is going to be 1.28. Or down here, negative 1.28. So that is our critical value. So we looked up. So it says, step 2, we're going to look up and compute Z star, which means we need to find in the Z table. We looked in the Z table in order to find an area of 0.100, and we found one really close. And in this case, our Z star is 1 plus or minus 1.8, which means the area under the curve between negative 1.28 and 1.28 will be, or is approximately 0.8%. This final step would be to interpret the findings. All right, and then we'll do that. We'll do that eventually today. So here's what I want to do. 80%. That means my tail area is 10%. Remember, it's going to be 0.20 divided by 2, which is 10%. In this one, we're missing 10%, so we're going to take 0.10 and we're going to divide by 2. That means the tail is going to be 5%. In this one, we're going to take 0.5. We're going to take 5% or 0.05. 0.05 and divide by 2. So our tail area is going to be 0.025. In this next one, we're missing 2%, so 0.02 divided by 2. Our tail area is going to be 0.01%. That would be for a 98% confidence. And for a 99% confidence interval, we're missing 0.01. So we got to divide by 2, and we get 0.005. So what do I tell you? What am I trying to tell you? Let me give you this diagram real here quick beforehand. And just draw in a line here. And we'll call this minus Z star. And this up here will be at the exact same place on this side. We'll call this a positive Z star, right? And the tail is 1 minus the probability over 2, right? Isn't that what I just did? 1 minus the probability over 2. I took 1, I subtracted off 0.8, I got 0.2, and divided by 2, and that gave me these values. And I'll be right back. So we know these z-scores are going to be plus or minus 1.28. Now I got to look up 0.05. So I'll go over here, go find 0.05. Oh, wow, that's right here in the middle between these two. So that would be 1.601234.5. I would say 1.645. Plus or minus 1.645. Now, I normally wouldn't do 645, but man, it's right in the middle, right? That's only 5 up, and that's 5 down. So that, to me, would be, I'll just do it that way. All right, so now we're going to look up 0.025 in the table. So we just keep going up, 0.025. There it is, right there, exactly. So that's negative 1.96. Negative 1.96. Remember how we always say it's 2? And I'm going to tell you right now, on your Regents exams, it's going to be 2. But in real life, it's really 1.96. Now, normally for 95%, we use plus or minus 2 standard deviations. But it's really 1.96. It's really close, but it's not really 2. But as far as the Regents exam goes, they're probably going to want you to use just 2. Because they're not as high-tech as we're getting today. Now we're looking for 0.01. And that's probably this one right here. Negative, I'm going to guess that's negative plus or minus 2.33. So plus or minus 2.33. And this last one's going to get funky. Let's see what that one is. What are we looking for? 0.005. And that would be like right here in the middle between these two. So that would be 2.575. So plus or minus 2.575. So those would be our Z-star scores. Now by Z-stars, those are just our critical values, which will ensure that the center will be at the confidence level that we are looking for. Okay? All right, I'll be right back. Nope, no, we can keep going. So what are we doing here? I'm missing something. Oh, I don't think I left enough room for all the notes I wanted to put in here. Confidence level for a population. For a simple, I'm going to write small. For a simple random sample of size n from a population, I'm going to abbreviate too, population having an unknown mean mu and a known standard deviation. Remember, when you get to AP stats, they're going to take that away from you. And a known standard deviation sigma. A confidence level P. I think this was our AP stats teacher uses this. A level P confidence. Let's call it a level P confidence. I don't know why we're using P. I'm not really sure I like P very much. For mu would be X bar, let me do this in a different color. X bar plus or minus Z star. So this tells you how many standard deviations we go. And so if that's how many we're going to go, we need to take that Z star, whether it's 1 or 2 or 1.28 or whatever, and multiply it by our standard deviation. Well, our standard deviation for sample means is the square root of, is the population standard deviation divided by the square root of n. And this is where Z star is the critical value well, let's say is the z-score associated with an area 1 minus p over 2 in the tail of the normal distribution. In the tail of the normal distribution. And that's what we just did, right? We're going to go through what that formula means in a minute. So here's one last thing, and this is just a little bit overkill. If we know that the population is normal, then this interval is exact. However, for most of the time, so long as n is large enough, the interval is approximately correct. Really close. And remember, the larger the n, the better we're going to do. All right, let's just go through an example. Let me take a pause and I'll come back and do an example. So Dr. Andrews has just created a new drug that will increase the level of antioxidants in the human body. Unfortunately, the levels are not precise, but repeated measurements of the levels were found to follow a normal distribution almost exactly. The mean mu for the population is not known. The standard deviation of the distribution is known to be 2.04 milligrams per pint. Dr. Andrews took 5 measurements from her patients and recorded the results below. We want a 90% confidence interval for the true level of antioxidants, mu, in the patient's body. Woo! That sounds complicated. Let's go through the procedures. Where's our procedures? Step 1. Take a sample and calculate the mean. So the first thing we're going to do is take an average of these two numbers. So let me get out of this. See if I can figure out. There they are. I can do it this way. So we're going to do 276.58 plus 273.12 plus 275.04 plus 268.98 plus 272.56. Now, I think it's important to tell you we only collected 5 data points, but remember it said that my population distribution is almost exactly normally distributed. So I can use almost any n value I want. So 5 is just fine. As long as my population is known to be normally distributed or almost exactly normally distributed, we're good with 5. Otherwise, we'd need more n values, or we need more values of n. So we're going to take that, enter, and divide by 5. So I'm going to get 273.256. So we calculate the x bar, step 1. Find x bar. So find x bar. And we found it to be 273.256. All right, step 2. We want to find the critical values. So we need to find Z star. Now we want a 90% confidence interval. Well, therefore, we need 10%. Oh, not 10%. We need 5% in the tails. All right. So you can either look it up or we can go to the previous page and find out what's 5% in the tails. 90%, we need a Z star of 1 point, it's right here, 1.645 is going to be our Z star or our critical value. So our Z star is 1.645. Now I could have gone back up and looked it in the tables, but there it is. Now, step 3. What was step 3? Calculate and interpret the interval. So let's do that. So our interval is going to be X bar plus or minus Z star times the standard deviation. Really what we're going to multiply is the standard deviation of X bar. And remember, the standard deviation of X bar is equal to the population standard deviation divided by the square root of n. Or in other words, what did they say the standard deviation was here? 2.04 divided by the square root of 5, which is 2.04 divided by, oh, you guys can't see those numbers. They're right behind my head. The square root of 5. So that would be 0.9123. Probably close enough. All right, so what's my interval going to be? Well, my interval, do I have room here? I think I do. I do have plenty of room. I need to take some more of that. I want to create my interval. So my interval is going to be X bar plus or minus Z star times, so my X bar we said was 273.256 plus or minus 1.645 times my standard deviation of 0.9123. So we got to figure out what these are. We're going to figure out what these are. So we're going to take our calculator out. This. There we go. Plus 1.645 times this. So 274.76. Let's take that as the high number. 274.76. Now we're going to do the same thing, but we're going to subtract now, not add. And I get 271.76. So this is my 90% confidence interval. Now I got to make sure I understand what in the heck that means. What does that mean? So let's just say this. Okay, we're going to try to say this. We are 90% confident that the true level of, now I'm going to make it more meaningful to this problem, and I'm not going to be able to spell antioxidants. I knew it was coming up. Of antioxidants in the population lies between 271.76. Now these were milligrams, right? Or milliliters. What are these things? Oh, I probably should have been better with these. I'm going to go milligrams per pint. Milligrams per pint. I don't remember what my units were exactly. 274.7. I should have been better with my units there. All right. So that's it. We are 90% confident that the true value of the population, I should have written population mean, lies between 271.76 milligrams per pint to 274 milligrams, 0.76 milligrams per pint. That's all we know. That's our window of where we believe, we're 90% confident, where we believe with 90% confidence that our true mean is. All right, so if we take a look back at example 2 from the previous effect of a 90% confident, what would there be if we only had a single measurement of 273.16? So if we just had a single measurement. Now, let's try this. We have an X bar of, what was our X bar? 273.256. 256. But now we have to use our standard deviation of 2.04. And we have our z, which our z-scar is not going to change. That's still 1.645. Now let's see what our interval looks like if we only have one measurement. One measurement. So we're trying to figure out, using one measurement, what will be. So we take x, so we take 273.256, you can probably say, put 23 there, plus or minus the z-scar, which is 1.645, times 2.04. And we'll do that in our calculator. It's very close to this. Enter. We just got to get rid of this last one. And put 2.04. Enter. And we'll put plus. And our answer is going to be 269.9 to 276.6. 276.6. Now, what happened to it? Did it make it wider? It went from 271 to 2 down. Now, the reason it didn't go down much, take a look at this. This is because our original was approximately normal, and we had already had a relatively small standard deviation. But it did widen it up. Actually, it widened it up quite a bit. It actually widened it up quite a bit because it went down almost 2 and up almost 2. So that's another full standard deviation. So it had to widen it in order to gather that. So by doing one. All right. So let's try another example after we take a pause. So this is your opportunity to try to be successful, okay, kids? You're wondering if I'm going to give you those formulas on the quiz? Absolutely. I'm absolutely going to give you those formulas on the quiz. And on the Regents exam, we're going to talk about what the Regents exam is going to ask. We're doing a little overkill on this, and when we come back and we look at what the Regents exam's asking, we're going to really understand exactly what they're asking about, and then the problems are going to be relatively paltry compared to what we're doing, okay? But I think this is important that you do this the right way. So right now, this should give you an opportunity to try one on your own. So pause it and then come back. I'll give you a good face to look at. I don't know why I did that. That's kind of stupid. Hopefully you're back. Hopefully you pause it. United States Army is trying to determine the effectiveness of some of their current training regulations. In order to begin their assessment, they need to determine the average number of years a soldier with the rank of captain has been in their current assignment. Since there are approximately 72,000 captains in the United States military, and I think I looked that up, that's true, it should say the United States Army, it would not be feasible to survey them all. Certainly would. So Corporal Capon was tasked with collecting a simple random sample of only 120 captains. Now, that's a large enough sample that we don't really need to worry about whether or not it's that normal or not, because it's a large enough sample. It's pretty big. What she determined was the mean time served in their position was 2.3 years. And she was provided with the fact that the standard deviation was 0.4 years. Now, remember, we have to give that to you because that was beyond the scope of this year. All right, so let's go through. What do we need? Step 1. We got our X bar. She calculated it to be 2.3 years. We have our N value. Our N value is 120. we have our standard deviation, our population standard deviation of 0.4. So I think at this time it'd be prudent to get the sample standard deviation. So we're going to do, and let's see, 0.4 divided by the square root of 120. Boy, that's going to be tiny. So, shoot. So 0.4 divided by the square root of 120. So I got 0.0365, 0.0365. All right, so that's step one. We got pretty much that. Well, wait a second. What kind of confidence interval? We want a 95% confidence interval. So I'm going to pretend like I didn't make that table on the other chart. That means I need 5% left over in the tails. If I divide that by 2, I get 0.025 left in the tails. So I'm going to go look at the tails and find 0.025 again. There it is right there. And if I remember correctly, that's negative 1.96. So my Z star is equal to 1.96. Now, on the Regents exam, I'm going to tell you right now, when they ask for a confidence interval of 95%, I want you to use 2. I want you to use 2, because this is 1.96, but I know the Regents, they try to simplify things, and they're going to want you to just use 2. So we want a 95% confidence interval, though. So now we're going to set up our confidence interval, and we're going to take, so we found our Z star. This was like step 2 over here. So step 3, last step, we're going to take our X bar. We're going to find our interval. X bar plus or minus Z star times the population times our sample. I was just going to do that. Sample standard deviation. Okay. So this is going to be equal to, what do we got? 2.3 times, or excuse me, not times, but plus or minus 1.96 times the standard deviation of 0.0365. So we're going to figure out what this interval is. Excuse me. I'm just going to give it to you. If you type that in, you get 2.23, comma 2.37. So now we got to write a statement. You have to interpret your results. So we are 95% confident that the true true population mean mu, mu of the average number of years a captain remains in their current position is between 2.23 and 2.37 years. So the average, we are 95% confident that the true population mean, which represents the average number of years a captain remains in their current position, is between 2.23 and 2.23 and 2.37 years. Wow, that's hard to say twice fast. All right, one more page and we are done. Okay, here's the last thing I'm going to teach you. And that's like, we need to determine the appropriate sample size in order to get a desired margin of error. What are we going to do? It would be kind of dumb to start to create a survey, collect data, perform calculations, submit your interpretations to be told later by your employer that they wanted a higher level of confidence. right? You go all this work, and they say, wait, you're only 90% confident? I want to be 98% confident. Go back and do it again. What? So, so it's not like you can change what you did, right? You can't go, oh, wait, hold on. No, I actually didn't do that. So the only way I can increase or decrease or determine the confidence level, and the only thing I can adjust is my value of n. So most wise statisticians will start with their planning. They'll determine the desired level of confidence that they want, and then they start surveying. Because if I know that I need a 98% confidence interval, then I know that I need an n value large enough to give me a 98% confidence interval. Okay? So let's say that Dr. Andrews would like to have a margin of error of 0.010 with a 95% confidence level or confidence interval. How many survey/measurement/tests must be in the average in order to ensure the interval meets the margin required? So recall that the margin of error is equal to, did we talk about this? I think I talked about this a little bit. I don't know if did I address it in this? I might have missed it. Okay, it's not going to be recall. I think it's going to be for the first time. The margin of error is defined as this value right here. It is z star times the sample standard deviation. And we want this to be less than or equal to 1.2. I'm sorry, I just had to look something up. This number was wrong. I don't know where this number came from. It should be 1.2. All right, so we want to have a margin of error less than or equal to 1.2. So simply sakes, all we got to do is set this equal. Now, it's not that easy. It's z star times the population standard deviation divided by the square root of n is less than or equal to 1.2. So all we're going to do is plug in the right values and see if we can figure out what this is. So we know we got our z-star score of 1.96. And we're going to multiply by our standard deviation, our population standard deviation of 2.04, divided by the square root, that should be a square root, not a sigma, the square root of n. And we want that to be less than or equal to 1.2. All right. So how am I going to solve this sucker? I think probably, I don't know. On the left side, really what I have is 1.96 times 2.04 all over the square root of n is less than or equal to 1.2. That's really what I got on the left side. So I guess if I just cross multiply, I guess I could cross multiply. I hate doing that I'm just going to multiply both sides by the square root of n. I think that's just easier. Multiply this side by the square root of n, multiply this side by the square root of n. So these cancel, and so now I've got 1.96 times 2.04 less than or equal to 1.2 square roots of n. And now I'm just going to divide both sides by 1.2, divide by 1.2. So what I get now is the square root of n has to be greater than or equal to 1.96 times 2.04 all over 1.2. In this case, square root of n has to be greater than or equal to, and what do I get here? 3.332. If I square both sides, I get n has to be greater than or equal to 11.1. So be careful with the way you answer this. N has to be bigger than 11.1. So in order to get a confidence or a margin of error that is 1.2, I need to make sure that I use a n value of 12. Because if I used 11, it wouldn't quite be big enough. So how did I get all that? Well, I wanted a 95% confidence interval. The 95% confidence interval gave me my z-star score of 1.96. And then I just used my sample standard deviation, and I plugged it into this formula. So what you need to remember, the formula that you're going to use is that when you want to choose your sample size, it's Z star times standard deviation of over the square root of n has to be less than or equal to m, where m is used as your margin of error, whatever your margin of error is. So now if you want to, this will yield the minimum value of n. And solving for n, the square root of n, you're going to end up getting z star times sigma over m, and it has to be square root of n. So that's really when you solve it, you just really basically cross multiply. But when you get done, that's what it's going to end up being. But that's the formula you're going to use. So you know what? I think I should give you one more example. I don't have one in my book right here, but I'm going to make up one. Let's say we wanted a margin of error. This might come back and bite me in the butt. Margin of error of 3.65 with a 98% confidence interval. And we know our standard deviation, our population standard deviation is 6.2. So I need to find a confidence interval. Well, the first thing I got to do is figure out what my Z star is. So my Z star is going to come from my confidence interval here. So we're going to take 98%. That means 0.02 divided by 2 is in the tails, or 0.0100. So I go over here and I look at my table, 0.0100. This is 0.011. That's 2.33. So my Z score is going to be 2.33. So my Z star is 2.33. So now I'm going to use my formula. 2.33 times 6.2 divided by the square root of n has to be less than or equal to a margin of error of 3.65. So I'll multiply both sides by the square root of n. These cancel. And then I'm going to end up dividing by 3.65. So I end up getting, this won't let me drag. I end up getting the square root of n is greater than or equal to, notice the greater than or equal to is pointing at the n, greater than or equal to 2.33 times 6.2 divided by 3.65. This isn't going to be a very big number, so that's okay, I guess. I don't know what this is. 2.33 times 6.2, enter, divided by 3.65. So we get an n, let's see, it's almost the same as before. The square root of n is greater than or equal to 3.9578. And then we're going to have to square that. So we'll just square it. And we get 15.66. So n has to be greater than or equal to 15.66. Who cares? 4. So my n value in this case would have to be 16. All right, I hope that makes sense. That's how to pick an n value that will guarantee you a certain level of confidence with a certain level of margin of error. Okay, that's the end. Well, I'd say that's the end of the year, but I still have the practice test to go, and we still have the actual test to go. So, study, study, study. Get this stuff down. You'll be given some of the formulas, and we'll be doing quite a bit of review in class, okay? And I'll have a review. For those of you that aren't in my class, we'll have a review up in a few, 2 weeks probably, a week and a half. Maybe next weekend. All right, have a great weekend. Well, have a great life. We're going to be starting review real soon. I'm going to put a ton of review up online. Make sure you hit subscribe. Hit the bell next to the word subscribe so you get notifications of when I'm going to go live. That way, if you've got time, you can log on. You can pull out your phone. You can check out what we're doing. That's it. All right. One more day, one more video, and this year is over, except for review. And we got a ton of review, so it's not quite over. Goodbye.